interrupt. The sound's going in and out online.
Okay. Oh yeah, that's much better. So a bit on the background. So for a very long time, the CSVC for us was basically this, a drawing, because it was physically impossible to access the real thing. So we based most of our design of those engineering drawings, and used those to build our own understanding of what the CSVC was like. Which, I mean, you've seen the pictures of it now. We also had some very old pictures of it to verify what we found. The few things, so we had this, but then the problem is there were quite a few unknowns with that. For example, some of the dimensions, especially the lid, we didn't really have the drawings, we only had photographs. So we had to estimate quite a few things there. The seal condition, and also the whole configuration on the inside, especially towards the bottom end, this Teflon cap. We didn't really know where it was positioned. It could be, there could have been a gap there or no gap. Turns out there was no gap, which could significantly affect how the piercing was going. And also the bottom wall, we just had engineering drawings. So we knew there was a tolerance of 5,000 of an inch on there. Doesn't sound like much, but the original thickness is 20 thousandths of an inch. So that's quite a big difference, and that affects the piercing dynamics. What we also had to work with was that. So that's some, that's actually a piercing tool that was already built and used for the gas analysis sample container, which contained a scoop sample from Apollo 12, 12024. This operation was carried out, although it was not successful because the container had already leaked, and but we did have the images of the hardware that was used for that. And turns out what we designed in the end, well, it's pretty similar. It's just bigger to fit the CSVC. So what we have is basically a big vacuum chamber, which contains a holder that is designed to fit around the CSVC. Problem there is, since we didn't know the exact dimensions, well, we had to take basically design the whole thing to account for quite a bit of variation in more or less all the dimensions of the CSVC to be sure that, well, it would fit in there, because we only had one try. Then you also have a spring in there just to be sure to position everything properly, and you have the piercing dip, or as Ryan would call it, the chisel, that sits there in the bottom, and that's actuated manually by cranking the screw. Here you can see a bit more details of the design. I'm not really going to go into it. If you want to know more, I'm happy to discuss it later on or during the discussion round. What I really want to talk about, and that's not been talked about too much yet, is how we actually made sure that this would work. So how the whole verification validation process went. So we did two main stages. The first on the left was a prototyping stage. So we used 3D printing and COTS material to build the first prototype of the system to see if the principle itself could work and do some adjustments if needed. So that was our first series of experiment. And then when we were happy with what we had there we progressed to the actual final build, which was then also extensively tested in the second round of testing. What we also built was a mock-up of the CSVC. Especially what was especially important to us was the bottom end. So we had those screw-on caps that were calibrated to have the maximal and minimum thickness that we're expecting the CSVC to have. So we could simulate both scenarios. We also did some machine Teflon caps, replicas, that were also interchangeable, and that also allowed us to test either for the presence or the absence of a gap between the Teflon cap and the bottom surface. And so using those things, we did our first round of testing during the prototyping, where there it was more to focus on the operations, just check that everything worked as we intended it to work, but also on determining one key parameter, which is the length of the piercing tip. Because if it's too shallow, well, you're just not going to pierce. If it's too long, you're going to pierce, but you're also going to pierce the underlying Teflon cap. And then the creation team was going to have a lot of problem of extruding it, and also we may just contaminate the sample. So this is what we had during the final prototyping runs, we're pretty happy with that. As you can see, the steel was pierced adequately, but we had the Teflon cap which was barely indented. And so then we moved to final production. To validate the final design, we did, again, 2 types of tests. We did tests in atmosphere, just to confirm that what we learned from prototyping was actually true. So we did a series of 15 tests, again, with different thicknesses, with the present or not of Teflon cap. And we also had 2 different piercing tip geometries we were interested in. And then what we also did is piercing under vacuum conditions, and also just to show that everything was working under UHV, that the system was able to retain UHV, and also to see if pressure differential between the CSVC and the vacuum chamber would affect the piercing. And so in the end, we were quite confident with what he had, that it could, our piercing tool would work in all the scenarios that we had envisioned, at least, and also that we had identified a piercing tip geometry that seemed adequate. Those are some of the results. Again, that's like some of the final piercing tests we did, where we're pretty happy with the results. That was done under vacuum, and you can see you still get a pretty nice hole without damaging the underlying Teflon. From then on, we then went to the piercing campaign itself at JSC, which was a bit nerve-wracking, obviously, because you only have 1 shot of doing that. And yeah, it's also already been discussed in quite a lot of detail, which is good because I don't really know if I have time to go into it. But yeah, basically bottom line is we achieved that, which was considered a success, because as you can see on the left, on the XCT, we pierced a decent hole in the bottom of the CSVC without penetrating the Teflon. We did dent it a bit, but that's acceptable. You can also notice that the hole in the bottom looks pretty much like what we had during testing, so we're also happy with what our validation process did. Another thing to notice as well, we don't see on the XCT at least any shading of material, which could also have been a concern, because we're piercing stainless steel with stainless steel. It's different harness, but still there could be a risk of dulling or shading of some material. I'm now going to go a bit into the lessons we learned from that. And also the good thing here is it worked. I think that's the main lesson, is it worked. Otherwise this conversation would be much harder to have. But we still identified a few things we could have improved, I think. I think first of all, the piercing tool was pretty large in volume. It had a lot of material, which made pumping evacuation times quite long. It was sometimes difficult to manipulate. So sorry, Julian. But yeah, it was pretty bulky. So it was workable, but in the confine of the glove box, like that, there was some wasn't optimal to handle. And it took us quite a long time to get there. It took us almost 2 years to go from the early concepts to the final piercing operation. We think we identified what the causes of those were. So I think the main cause for the large volume, the fact that it wasn't very optimized, is just because we weren't sure about the CSVC itself. So we had to take in margins, precautions, and so yeah, like ergonomy came last, for example. There were also a few problems, I think, about I think the 2 last points can mostly be formulated as just don't do this during a pandemic, which I've heard before during this week. Some information flow was a bit difficult because obviously we had different organizations. We were like on different continents, which didn't help. And also some lead times just set us back by yeah, like 6 months at a time. And so for future activities, what we'd propose is mostly focusing on this lack of information we had on the hardware. So we think we have 3 points. The first one would be when designing those sample containers, maybe involve the science teams as soon as possible, so that we can preempt the fact that we're doing something, that the science team are doing something with a container which wasn't really thought of before. And also add some interfaces, which may maybe sound redundant, but that could actually help downstairs. For example, if the CSVC had an obvious place to grip it, that would have really made our life easier. One thing we'd also advocate for is having better or generate more data on the tools and on the equipment and on the containers by, say, measuring all the individual parts accurately. Also capture some more data on their life cycle and store them in a digital format. We've seen a few different talks, whether it's about the Apollo audio and video material, or we've also just the previous talk was about a digital platform for sample information. Well, we could maybe do the same thing with equipment catalogs. And the final one would be whenever we manufacture some of that critical equipment. I mean, the design takes a long time to make, but once you have them, you may as well manufacture loads of it, so that engineers and scientists down the road have more, basically have blank versions of that equipment that they can use for testing, that they can use maybe even to inform the science, to see how the materials evolve and may have affected the results. So yeah, basically, that's just highlighting the point I just made. I think we want to move from just having manufacturing drawings on paper to digital formats and also to physical copies of all the as much hardware as we can. So that brings me to the end of my talk. I'd like to acknowledge the rest of the ANGSA team we've worked with, especially the people from Washington University and the people from Curation who did an amazing job at finding those old drawings without which it wouldn't have been possible at all. And also personally, I'd like to thank Survey for their travel grant, helping me to attend this conference, and also the European Space Resource Innovation Center allowed me to participate. They also contributed financially. Thank you very much.